Hey everybody, and welcome to the third and final installment. That ding means you're in the right place. The third and final installment of the quantum model of the atom, part 3. I'm excited for you guys to join me and take a journey through the remainder of this PowerPoint. We're going to learn about a little more about where electrons live, but we're also going to learn about why trying to find where they live is a little funky. So, without further ado, let's continue with the Heisenberg uncertainty principle. Yes, Werner Heisenberg. Werner Heisenberg. He said it is impossible to determine simultaneously at the same time both the position and the velocity of a moving particle, or in this case, since we're talking so much about the atom, an electron. Werner Heisenberg said you cannot simultaneously at the same time tell the position and the velocity of electron. You cannot do it. You can find the position. Yes, I know, computer. You can find the position, but you can't tell the velocity. You can find the velocity, but you can't tell the position. You cannot do it at the same time. So, this is due to the fact that simply by observing, just like in the double slit experiment, simply by observing an electron, the measurement itself of observing will cause that electron's position to change. Okay? Light will interact with the electron and cause it to move. So, what did scientists do? Because scientists are smart. Scientists wanted to try and figure out a way around this. So what did they do? Well, they said, we're not going to pinpoint an electron. Oh no. We are going to instead use probability and regions. Think about it this way. You're at school. Now, if we ask someone in your house, where is little Johnny today? They're going to say, well, Johnny's in school. Do they know exactly where Johnny is? Do they know exactly what class he is in? No. They don't know his exact location, but there is a high probability that he is in school. There's a high probability that maybe he's in the science hallway or the English hallway. So we can't tell the exact location of an electron, but we can look at a region with high probability of finding that electron. Werner Heisenberg, the Heisenberg uncertainty principle, you cannot simultaneously tell the position of an electron and its velocity. Can't do it at the same time, cannot do it. All right, oh, funny joke, right? There's Werner Heisenberg, just in case you were curious. So Werner Heisenberg is out, he's driving his car, he's having a good time. He's speeding down the road, then all of a sudden he hears the police behind him. They're running their siren. The officer pulls him over and he says, "Excuse me, sir, do you know how fast you are going?" And Werner, oh boy, Werner Heisenberg, you know what he says? He looks up to the officer and he says, "Well, no, officer, I'm sorry, but I know exactly where I was." Oh man, if you're not laughing, I don't blame you, because that really wasn't that funny of a joke. But it's okay, because if you understand the Heisenberg uncertainty principle, you understand this joke. He doesn't know how fast he was going, but he knows where he was. You can't tell speed and position at the same time. Cannot do it. All right, continuing on, let's see what else we got. Oh yes, Schrodinger's wave equation. This PowerPoint is full of gentlemen with interesting names. Werner Heisenberg, Erwin Schrödinger, or Schrödinger. Now he came up with the wave equation. This is his wave equation, and you need to memorize it. You have to memorize it. It says it right there. You know your old teach, he's full of jokes. Just kidding, you do not have to memorize this equation. But this equation allows us to calculate the wave function of a particle. So we could plug in some variables here with the information of a particle, of an electron, and we can calculate the wave function of it. Okay? We can calculate the wave function of it. Erwin Schrödinger was an interesting fellow. He came up with, he proposed the theoretical thought experiment of Schrodinger's cat. Now, if you're curious, I definitely suggest you looking it up. It is really interesting to think about. If Schrodinger proposed that if he took a cat, put it in a closed box with a vial of poison and a radioactive material, that as the radioactive material gave off radiation, it would trigger a mechanism to break the vial of poison. And sadly, that would kill the cat. But he theorized that with the box closed, you can't tell whether the cat is alive or dead. And in essence, it's both alive and dead at the same time. It's really something weird to think about. Maybe I'll link one of these videos up at the very end. It goes into a little more depth on explaining it, but he actually explained it as being a joke because he thought, without cluttering this too much, that when someone else had proposed an idea that it was kind of silly what they proposed. So he's like, well, I'm going to propose this silly idea too, to kind of make fun of what you just said. But it's something that, everybody kind of remembers and we're talking about in a high school chemistry classroom. So kind of interesting. All right, continuing to move on. So a little bit more about Schrodinger. The equation describes the wave properties of electrons and other small particles. And it was so monumental. It was so magnificently important because it did one major thing. Now, I want you to think back. Think back to Bohr's model of the atom. There were three great things, but there were two very things, right? One, scientists couldn't understand why the levels were quantized. And two, it only worked for hydrogen. Well, Schrodinger's wave equation, boom, right there. It proved quantization. It helped to prove the Bohr model of the atom. It helped to prove that electrons existed on these energy levels, on these orbits, and when they were hit with a photon with energy, they jumped up. But then they fell back down and they emitted that photon. See that photon right there? Boom. Only waves of specific energies, right? Quantized amounts and frequencies came out of the equation, and it describes the arrangement of electrons in atoms. Continuing on, let's see. So together, the ideas of quantized levels of energy, the de Broglie wave properties, Heisenberg uncertainty principle, Schrodinger's wave equation, all of these laid the framework, helped to prove the Bohr model of the atom, but laid the framework for the quantum mechanical model of the atom. And this is where we will actually stop our discussion of what the atom looks like with this model. We're going to make one more adjustment to our model, and then this will pretty much be it. We went from Democritus to J.J. Thomson to Ernest Rutherford to Bohr. Now we're going to get to the quantum mechanical model. Without further ado, ladies and gentlemen, I'm going to present to you the quantum mechanical model of the atom. It's also known as the modern electron cloud model. It shows the electrons orbiting around the nucleus in specific regions of high probability, or electron clouds. Okay? Regions, no longer are those electrons located on these orbiting paths. No more. They are now in regions. And what do those regions look like? Well, no, we don't have to look at this. Those regions look like this. We have an s orbital, one type of p orbital, a second and a third type, and when you put those together you get this kind of like flowery design, but it's actually the x-axis, the y-axis, and the z-axis is coming out straight towards you. So these are orbitals. Well, what exactly is an orbital besides just a region of high probability? Let's see. So an orbital is a three-dimensional region around the nucleus that indicates the most probable location of finding an electron. If you have a higher electron density, your probability is high, and if your probability is low, that means you have a lower likelihood of finding an electron, or a lower electron density. It's very important now. These words are close, but it's very important to understand that orbital and orbit do not mean the same thing. They are not interchangeable. They do not mean the same thing. An orbit is similar to an energy level or a path. An orbital is a region, a three-dimensional region. And there are several different types of orbitals. You guys just saw that. The s orbital, the three types of p orbitals. And then we can break that down even further in just a second. Here's a depiction of an s orbital. Now it's kind of hard because this is two-dimensional, but think of this as a sphere, right? Think of it as a sphere, okay? That s orbital is going out towards you, away from you, top, bottom, side to side. Here's your little nucleus, and here's your s orbital all around that nucleus. And notice this is showing the probability aspect of it. We have a high probability in that area, and as we go further out of the orbital, the probability is lowered. The electron density is lowered. Now, an electron can be anywhere in here, but the probability of us finding an electron in an s orbital is highest right in this red area. There's a 2s orbital. And what this means is here we have our little s, and then here's a second bigger s. So, if I were to say to you, hey, would it be more likely for you to find an electron here or here in between? You'd say right here, right? It's a higher likelihood, a higher probability of finding that electron. You may be familiar with this from the past picture. This is a p orbital, more specifically a py orbital. It's going straight up and down. We could tilt this on its side, that would be a px, or we could point it straight out at you. That is a pz. When we combine those together, we get something that looks like this. Now there are 4 different types of orbitals. There's the s orbital, the p orbital, the d orbital, and the f orbital. Now, for an s orbital, we only observed one type. For a p orbital, we observed 3 types. See if you can follow the pattern. 1, 3, 5. Very good. For a d orbital, we would assume 5 types, and for an f orbital, we would assume 7 types. And that is exactly what we have here. 1 type of S, 3 Ps, 5 Ds, 7 Fs. Now, how are we going to remember S, P, D, and F? Well, I have a fun little way to remember that. Some penguins do or don't fart. Yes, even penguins have flatulence. It's not a joking matter. I should have made an infomercial for the tragedy of penguin flatulence. Yes, silly, but you will remember it that way. S, P, D, and F. Another interesting thing to go on about this, and we'll learn this a little bit later, but each of these orbitals can hold 2 electrons. So this orbital can hold 2. The px can hold 2, the pz can hold 2, and the py can hold 2. So the s can hold a total of 2, the p can hold a total of 6, the d can hold a total of 10, and the f can hold a total of 14. Now, that might not seem that like, oh my God, wow. However, if we take a look at the periodic table, right here, I'm going to take you guys along with me. If we take a look at the periodic table, we see the periodic table is broken up into groups. 1 second, guys, just adjusting this. There we go. These 2 columns right here are the s group. Remember what I told you? An s can hold 2 electrons. 1 column, 2 column. Jump all the way over to here. This area, 1, 2, 3, 4, 5, and 6. These 6 columns are called the p group, or the p block, sorry, the p block. A p can hold a total of, yes, computer, a p can hold a total of 6 electrons. Do you remember how many a d can hold? Correct, 10. This middle area is the d block. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And that just leaves this area down here. This is the f block, and they should have 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Now you may be saying, what about these 2? Well, these 2 actually belong right here. So that is the P block, and it has 14. See, chemistry is a wonderful subject because it is all intertwined. It all connects. So hopefully you guys are enjoying this as much as I am. I hope you guys enjoyed the video. I hope you guys enjoyed the rest of your PowerPoint. Make sure you study up because you do have a quiz coming up. And please let me know if you have any questions. And I will see you guys in the next installment of As the Chemical World Turns. That's it. Have a great day, everybody. Bye-bye.